Hello everyone, welcome to the inaugural lecture of your new NPTEL course Overview and Integration of Cellular Metabolism. The first lecture is about the very basic and the very generic concept of bioenergetics. As you have seen already from the course outline, we will be for the first couple of weeks we will be dealing with the general concept, then we will delve into the deeper metabolic pathway. So, in this lecture we will be covering the following concept, that will be we will learn how to define bioenergetics, we will be learning the laws of thermodynamics as well as the thermodynamic variables, that is also known as thermodynamic quantities. We will understand the very important concept of standard free energy change and how it is related to equilibrium constant, also another important concept. Also we will be learning a very important biological phenomena by which we can couple multiple enzymatic reaction using thermodynamic coupling. So, let us start right away. So, what is bioenergetics? Bioenergetics actually deals with energy flow, how energy flows and it is transformed in various forms across biological systems. This is the very basic definition of bioenergetics. Now, it can include multiple things. Considering a living system, generally we obtain energy from food, various sources, plants obtain energy from sunlight, and by our various physiological processes we actually transfer this energy into various forms. And before transferring the energy, in case of storage forms, it might be held in a captive state in the cells and ultimately released when there is a functional requirement. So, this is the whole concept of bioenergetics. Now, giving you a few example how we can use the energy. As you can see from the list, it can include production of energy currency, that is ATP. We can use the energy in multiple metabolic pathway regarding transport of various molecular ligands, that is known as active transport. Energy is very important for muscle contraction, regulation of our temperature, synthesis of multiple compound, reproduction, the list goes on and on. All right. Also, for example, in animal firefly, this can be used in production of light, right. So, the fundamental law of energy transformation the fundamental phenomena of energy transformation is governed by laws of thermodynamics, that is the two laws of thermodynamics, and biological system are no exception, right. So, let us understand the laws of thermodynamics in a simple way. The first law of thermodynamics deals with, is known as law of conservation of energy. It states that energy cannot be created or destroyed, but it can be converted from one form to another. So, if we consider a closed system, the total energy remains constant. Okay. So, this is the first law. Energy can neither be created or destroyed, it can only be converted across various forms in a closed system. So, this law is actually easy to understand. The second law may not be easier to read. Okay. So, we have simplified the concept for you. It states that in energy transfer or transformation, okay, the total entropy of a closed system will always increase over time. So, very important concept of entropy is introduced in the second law of thermodynamics. What is entropy? Entropy is actually measurement of a randomness or disorderliness of a system, how random or how the system is in disorder. So, if we go inside the very atomic level, we will always find out whenever an energy transfer occurs across a system, ultimately if the transformation actually occurs, the resultant product will always have a greater disorderliness or randomness. Okay. So, when A is transformed to B, B will always have more entropy, it is more disordered. Okay. Now, having defined these two or having known these two laws of thermodynamics, we should now understand what are the thermodynamic quantities. So, what do we mean by thermodynamic quantities? There are three thermodynamic quantities, to be very precise. The first one is Gibbs free energy. It is denoted by the term capital G. Okay. It is the amount of energy capable of doing a reaction at a constant temperature and pressure. This is the definition of Gibbs free energy. Now, generally when a reaction is exergonic, it always loses free energy. This is the dictum. Okay, we are defining laws here. Okay, so when in an exergonic reaction, the energy change sign is always negative, and the change is denoted by a triangle delta. This denotes the change. So delta G means change in free energy, and the ultimately what negative delta G means, that is the system loses free energy. Okay, so this is the standard of an exergonic reaction. On the contrary, what is endergonic reaction? In which the system gains energy, the system gives free energy, and it is denoted by positive, I mean delta G. There is no negative sign before that. Now one thing you need to be very mindful, that is the unit of delta G is in joules per mole or calories per mole, depending on CGS or SI system, and the conversion unit, as we all know from our basic +2 lessons or even undergraduate lessons, that 1 calorie is 4.2 joules roughly, and 4.18 joules to be specific. Okay, mind it. There is a term that is exothermic and endothermic, that is often confused with exergonic and endergonic. We will be explaining every one of them. Mind it, if you are using a term gonic, G to remember is exergonic, endergonic, since it is G, always remember there is a change in G or delta G or Gibbs free energy. Okay, so the next thing, the next thermodynamic quantity is enthalpy. This is also another derivative of the laws of thermodynamics. So what is enthalpy? It is denoted by capital H. It denotes the heat content of the system. How much heat is present in the system? How do we determine how much heat is present in the system? It is denoted by the total amount and quantity of chemical bonds that are present in the reactant and product. Okay, suppose one chemical or A plus B is reacting to form C. So the amount of bonds, chemical bonds, that is present in A, that is present in B, that is present in C, will actually determine the total enthalpy. So imagine a reaction where A plus B is reacting to form C, and ultimately the system is becoming hot. It means what? We are losing heat. This reaction is losing H or heat, and it is denoted by delta H being negative, and this is known as exothermic reaction. Any reaction that becomes hot, the temperature increases while the reaction proceeds, is known as exothermic reaction. The change in delta H is negative, right? On the contrary, in endothermic reaction, there might be situation where a system, I mean compound A and compound B is reacting to form compound D, and what's happening? Heat is gained, means it is gaining heat from the surroundings, and ultimately the reaction system becomes cool. This type of reaction are known as endothermic reaction, and delta H change is positive. So again, in contrasting with the last slide, that is exergonic, where the delta G was negative, exothermic is delta H negative. Thermo means heat related to temperature. Okay. So this is the concept of Gibbs free energy and enthalpy. Now we come to a critical concept of entropy. So what is entropy? As I told you while defining the second law of thermodynamics, it is the quantitative expression of randomness or disorder in a system, right? And how is it translating to chemical reaction? As I told you, when a chemical reaction occurs spontaneously, the system gains entropy. It means the change in delta S is positive. Okay, it was quite different from previous two reaction. Generally, when considering delta G and delta H, spontaneous reactions are exergonic, spontaneous reactions are exothermic, means the change in delta G and delta H is negative, but when considering entropy, the change in delta S is always positive. For example, how will we measure entropy? The sum total of the entropy of product minus sum total of the entropy of reactant, sigma is the sign of summation. So this gives us the total entropy of the reaction. If entropy of the reaction is positive, this means and the reactant will be converted to product and the reaction will be spontaneous. So, there is an example where the entropy of the each and every molecule has been considered and ultimately it is found to be positive, that is 103 joules per calorie, because this is the unit of entropy, very important. So, here simple, the reaction is very simple, propane C3H8 combustion of propane. So, propane is combining with oxygen to get converted to carbon dioxide and water vapor or water. So, considering the total energy or total entropy of the product, it is more than that of the reactant. So, delta S is positive and the reaction will be spontaneously occurring. Mind it, one thing to remember is complex molecule will have more entropy. Why this is so? Because the more complex the compound is, there are multiple bonds and they have a multiple probability of adjusting them in multiple angles. So, they can twist and turn. So, this gives rise to more disorder. So, that is why a complex compound will have more entropy. So, what is the relation between these two? So, under standard or existing biological system, in considering a standard temperature and pressure standard condition, the rule is delta G equal to delta H minus T delta S. So, we have introduced another new term, that is T. This T, capital T, is the absolute temperature. Absolute temperature is denoted in Kelvin scale, degree K. Okay. So, mind it, this is not in centigrade or Fahrenheit, this is in Kelvin. So, delta G, that is the change in Gibbs free energy, delta H is the enthalpy of the system, T is the absolute temperature, and delta S is the change in entropy of the reacting system, and this is the reaction, how these three are related. Now, by convention, when entropy increases, delta S has a positive sign, delta H has a negative sign when heat is released, I told you, in exothermic, and delta G is supposed to be negative when the reaction is spontaneous or exergonic. Okay. So, equating this reaction, in case of a spontaneous reaction, the delta G is always negative. This is the rule. So, how can it be negative? If we equate the two in an exothermic reaction, so delta H, if this value is negative and this value is positive. Okay. So, the sum becomes negative. That is why if we incorporate or consider a spontaneous reaction where the value of delta H is negative and delta S is positive, by equating this relation, it always becomes negative and thus the reaction is spontaneous. So, considering how this whole thing is maintained in a living system, mind it, living system is not a closed system. We are not a closed system because we continuously react with our surrounding. So, if we just look at one organism and the laws might appear to be violated, but please remember, living system also follows these two laws of thermodynamics. It has to follow, because the corollary is we always react with our surroundings. If we consider our system and the surrounding, the exchange, then it becomes a closed system. Okay. So, how we gain energy? We gain energy from our surroundings in the form of nutrients or light, that is either food or sunlight, and we also return continuously the energy to the system in the form of heat. Maybe you are not feeling hot, but microperspiration, heat is constantly lost from our system, from the skin. Okay. But a cell is always isothermal, means the milieu, internal milieu of a cell is fixed, the temperature is always fixed. So, generally we can consider a cell to be an ideal system where a constant temperature and pressure is maintained. So, the only energy with which the cell has to deal with all its function is actually the Gibbs free energy. Okay. So, now let us look, let us find out what the Gibbs free energy allows the cell to do. It allows the cell to predict many things. Okay. Number one, whenever a chemical reaction is happening, I told you when change in delta G is negative, the reaction is spontaneous, it is always occurring. But when this change in delta energy stops, it means the cell has reached its equilibrium, means a reaction will not proceed in either direction. Okay. Next, the amount of work the cell can perform also depends on the total Gibbs free energy. And how does the cell at individual level, how do they gain the Gibbs free energy? there are multiple sources, there are nutrient molecule from solar radiation. Considering a plant, they are gaining energy from photosynthesis, okay. And what they do, they transform this free energy into some form with which they can readily use, by which they can readily use, and this is actually ATP, adenosine triphosphate. This is the ready made energy currency that can be used by a biological cell for performing multiple reactions, multiple phenomena. And since the biological cell is at a constant temperature, the laws of thermodynamics will also hold true. Now, let us learn a concept of equilibrium constant. So, what is equilibrium constant, or how is it denoted? Suppose two reactants A and B are reacting to form product C and D. The concentration of any reactant or product is denoted by a third bracket or a square bracket. So, if something is X, if I write X in square bracket, it means this is the concentration or amount per unit volume, okay. So, considering the concentration of the reactant and product, the equilibrium constant is denoted by this formula. The product of concentration, the product of concentration of the product, by one product I mean multiplication, and the one product I mean the reactants and products, okay. So, do not get confused between words. It is the multiplication of the concentration of the products divided by the multiplication of the concentration of the reactant, or product of the concentration of product divided by product of concentration of the reactant. This is the equilibrium constant, and we can assign any digit conventionally. K is assigned to any equilibrium constant for this reaction. So, we can say K1 is the specific equilibrium constant or equilibrium constant for this reversible reaction, okay. Now, another concept, that is standard free energy change. So, what is standard free energy change? We will see what is the exact mathematical formula. Now, first thing, something to know about standard free energy change. Often these are used interchangeably with the equilibrium constant, but they are not. They are actually closely related, but they are a bit different, okay. So, what the standard free energy change tells us? It tells us the composition of tells us that a reacting system will continue to react till equilibrium is reached, and it will gain or lose a amount of free energy. This is very specific for a reaction, and this is known as the standard free energy change. We know at equilibrium, so how, considering this reaction, if this reaction is at an equilibrium, means neither the reaction is going in any direction. It means what? It means concentration of the reactant and product will remain constant. The rate at which the reaction is occurring in forward direction is absolutely same, the rate that is absolutely same to the rate in which the reaction is occurring in the reverse direction. So, basically what happens? No net further change occurs in the system, okay. And as I already told you, the concentration of the reactant and product at equilibrium define the equilibrium constant. So, what is this standard free energy change? This standard, as I told you, free energy is always capital G, okay. So, and change in free energy is delta G. So, we have defined K, we have defined delta G. So, let us see how these two are related. Mind it, whenever we are saying standard free energy, it means this has got a specific symbol, it has got a 0 not sign. So, delta G not sign, okay. So, is an alternative mathematical way of expressing the equilibrium constant. If we state a standard free energy change of a reaction, and if we state the equilibrium constant of a reaction, we will get roughly the same idea as to when the reaction will attain equilibrium, at what time the reactant and product will be at the same concentration. But there is a mathematical relation, which is standard free energy change, or delta G naught, is equal to negative R absolute temperature and natural log of K, that is the equilibrium constant. So, what are these variables? Delta G0 is actually the standard change in Gibbs free energy. R is the universal gas constant, its value is fixed, 8.31 joules per Kelvin per mole, okay, and T is the temperature, okay, and K is the natural log of the equilibrium constant. So we can have an idea looking at the chart that if the equilibrium constant of a reaction is greater than 1, then delta G is negative. Why we are giving delta G prime sign? Because we are considering a specific reaction, okay. So delta G not prime is a specific free energy, standard free energy change for a reaction. So why this is happening? See, whenever we are considering the natural log of K, if the equilibrium constant is less than 1, the value of delta G will automatically becomes positive, because the log will be negative and the product of negative will become positive. And what if the equilibrium constant is 1, means the product of the reactants and the product of the concentration of the product is same, means equilibrium has reached. Then what is it? What does it mean? It means the standard free energy change is 0. So reaction is not proceeding in either way. If the delta G is negative, reaction has to proceed in forward direction. If the delta G is positive, reaction has to proceed in the reverse direction. So this is basically the rule between equilibrium constant and the standard free energy change. Mind it, a small, since both are exponentially related, a small change in delta G will have massive changes in the equilibrium constant, okay. Again, the unit of standard free energy change is kilojoule per mole. So here is a table where we can see the standard free energy change of various compounds. This is very important and will come handy at the later stage of the lecture and in the entire course of the course lecture, because it is very fundamental to understand the concept of thermodynamic coupling of the reactions. But for now we can remember some value, that is delta G prime of adenosine triphosphate, or the dissociation, the reaction where ATP dissociates to form ADP and PI is 30.5 kilojoule per mole. I already told you the conversion factor, so that is the homework for you. You can work it out what is the value in the CGS scale, okay. Considering this thing, we can see the compounds above ATP, that is phosphocreatine, acetyl phosphate, again dissection of ATP into adenosine monophosphate and pyrophosphate, it has got a huge amount of negative delta G. So this reaction is much more spontaneous and favorable compared to dissociation of ATP to adenosine diphosphate and inorganic phosphate. The terms ATP is adenosine triphosphate, ADP is adenosine diphosphate, PI is inorganic phosphate, so on and so forth, okay. And according to this chart, phosphoenol pyruvate, the dissociation of phosphoenol pyruvate will release the maximum amount of free energy. So this is highly favorable. So phosphoenol pyruvate always tries to dissociate, and compared to, so the compounds which are lower down the order will have less free energy change, okay. This ATP, as it is dissociating, some bond is breaking. This is actually phosphate bond. Since the breakage of phosphate bond is liberating so much high amount of energy, so these few compounds are known as, these few bonds in actually these compounds are actually known as high energy phosphate bonds. So we actually use the dissociation of high energy phosphate bond to utilize our own means of making a reaction or unfavorable reaction spontaneous. So this is a common example of firewood that we have studied in our NCERT books, textbook, physics textbooks in 5, 6, 7 nowadays, right. So what is this? Basically we are considering a concept of burning firewood, that is in our fireplace. So the normal reaction we already know, when wood burns, what happens? It gets converted to carbon dioxide and water vapor, because wood is a form of carbon, right. And is delta G changes large and negative, means wood always, the once started, wood will always continue to burn till the whole reaction is completed, right. It is a exergonic reaction, it is highly spontaneous reaction. However, it does not occur at room temperature, right. Why? Because it needs something that is known as activation energy. This is a very important concept. Just because when a substance A, in this case wood, will react with oxygen to form the next product, that is carbon dioxide and water, it does not mean it is spontaneous. So, we need something known as activation energy. This activation energy is actually provided by the match light. Okay. So, once we give a match light, it will catch fire and the whole reaction will spontaneously occur. This concept is actually used in enzymes. So, enzymes are biocatalyst. Whenever a product, two reactants are reacting, it might not be spontaneous. So, we provide some means by which the activation energy is lowered. We will see with an illustration. Just know this, for a reaction, for a product A to be converted to B, or for a product A to B to be converted to C and D, the delta G change is independent of the pathway. The path does not matter. Ultimately, the final product and reactant matter, and it depends on the initial concentration and nature of the reactants as the product. So, this is what an enzyme does. An enzyme, actually, see, this is an illustration where a ball will ultimately roll from higher point to lower point, but it cannot overcome this bump. It does not have that energy. So, enzyme does what? It lowers the bump. Now, the ball can easily roll over. This is the role that an enzyme actually does. They lower the activation energy. So, how we can actually use this concept in our biological system? We can use it very beautifully, because standard free energy change is actually additive. Suppose a compound has to transform from A to B and B to C. Ultimately, when we look at the bigger picture, when the compound is converted to A to C, there is a delta G for each of the reaction. When we combine the two reactions, the delta G value will add up. So, let us see how it is beneficial for our system. Okay, it is the algebraic sum of the total reaction. So, this principle is used for the very important concept, that is the crux of learning of today's class, that is a thermodynamically unfavorable or endergonic reaction can be driven forward by coupling it to a highly exergonic reaction through a common intermediate. These are few key terms: unfavorable, coupling with highly exergonic, and through a common intermediate. So, this is a very classical example. Mind it, glucose plus phosphate, that is converted to glucose, and inorganic phosphate, that is converted to glucose 6-phosphate and water. The standard free energy change is 13.8 kilojoule per mole, positive, not at all favorable. However, we couple this reaction with a common intermediate, that is inorganic phosphate. So, what do we do? We utilize ATP hydrolysis. So, when adenosine triphosphate combines with water to form ADP and PI, the reaction is highly spontaneous. The total delta G change is minus 30.5 kilojoule per mole. So, since these two reactions have got a common intermediate, that is inorganic phosphate, these two can easily be combined, and now the beauty of the law of thermodynamics is this: the resultant free energy change is negative, the reaction is exergonic, and now we can easily convert the reaction, we can easily go forward with the reaction. So, this principle has been used, is actually used in multiple steps, in multiple reactions that we will read in detail, where any endergonic reaction can be thermodynamically coupled with an exergonic reaction, and ultimately the final reaction can be done, is possible in the biological system. Mind it, the reaction 1 and 2 may be different, but net result is all that is matters. And if we look at the equilibrium constant, if you look in the terms of equilibrium constant, not free energy, again the product of the equilibrium constant is actually very high. So, generally 2 to 10 to the power 5 times it actually increases, and as we know, when equilibrium constant is in the positive side, the reaction is spontaneous. So, whether we equate it via equilibrium constant or we equate it via the standard free energy change, we can use the thermodynamically couple of reaction in all living cells. And the key possibility of this to happen is if ATP or the energy currency is available. If we can use the later reaction, then only we can utilize the former or the thermodynamic coupling of the reaction. So, the concepts to few facts to remember in this lecture is ATP is actually very useful for the basic, as a basic energy source, as we saw how it can help in coupling of various reaction. How do we produce ATP? If oxygen is present, it is produced by cellular respiration. If oxygen is absent, we produce it via the fermentation. And for quick burst of energy, body already utilizes the ATP that is present or that is made in the muscle by lactic acid formation, as well as very other metabolic steps that makes ATP. So, these are the few concepts that have been cleared in lecture 1. These are my references. Thank you for your attention.